Hello everybody, this is Salford University. I'm David Roberts. I'm joined by a class of undergraduate students taking virtual reality and computer games here today. So you should have the title slide of the TNA. So 131, Collaborative Exploration of Planet Mars. So we're going to start by talking about the high-level context here in terms of, first of all, the gap, the technology gap that we're looking at. Well, as you can see today, video conferencing isn't quite there yet. Even when video conferencing is working well, it's still a very long way away from being in the same place. Now, it's hard enough to do a presentation like this and get a feeling for whether or not the other people are enjoying, understanding, or even listening. So imagine trying to do distributed science or distributed command and control. The technology just really isn't there yet. Now, in particular, when you're in the real world, you can communicate through lots of different non-verbal communication. And presently, your various technologies are giving you different subsets of that. Now, there's many applications this applies to. And actually, we argue that at the moment, communication technology will only fit very specific niches like round the table meetings, conference meetings, etc. But it doesn't offer a general solution. There's a lot of applications that require a more general form of non-verbal communication. And the one that we're really working towards here is space and doing collaborative space science and collaborative mission control. So what's the research here? The research really is about telepresence. And what do I mean by that? Instead of just connecting two places so you can see into each other or hear what the other people are saying, actually bringing people into the same space to cohabit the simulations. So now we'll go into those three things in a little bit more detail. So starting off then with the technology gap. So a reasonable example of state-of-the-art of video conferencing is the Cisco system, which in theory is supposed to support some form of gaze. You have much better gaze support in more researchy systems like this one from Fraunhofer. And that is using what I would describe as a kind of virtuality where you're using a 3D computer graphics scene, you're building up avatars, you are sucking in video data from the real world to create those avatars. And the goal with this really is so that the camera looking into one space is aligned with the face of the person that you see from that face, from that space. And if that's correct, you should be able to support eye gaze. If it's correct in each direction, you can support eye gaze. And then, well, what's popular at the moment, UNC and also UCL and Barcelona are quite into robotics at the moment. This example from UNC is a shader lamp avatar where there is a robot that you're projecting the face onto using shader lamp technology. So that's kind of setting the scene. So, but we're going to try and do something that, to some extent, fits in the middle of these things. So here's where I upset our German partners by mentioning the war, which you're not supposed to do. But in this case, I think it's quite a good example. It is thought that the First World War, one of the large contributing factors to it, and certainly to it not being stopped, was confusion in a telephone conversation between the UK and Germany, a misunderstanding, and in particular a misunderstanding of intent. So spoken word alone, feeling of intent. It's not enough to give feelings of trust, etc. So this is probably the most famous example of when not using non-verbal communication has really caused some very, very severe outcomes. So what is non-verbal communication? Well, it's obviously things like gesture, posture, facial expression. It's interestingly also part of what is spoken is non-verbal communication. Even the tone of voice is classed as non-verbal communication. But importantly, while you can tell how somebody feels through looking at a photograph of them or a video, you can't usually pinpoint why they feel it, because in order to do that, you need to understand the spatial and the temporal context. So video conferencing at the moment gets the visual side across, it induces lag, and it loses the spatial component. VR has the potential to put that back in. More advanced kind of virtuality versions have the potential to do that with images. So you can see what somebody is looking at, what they're looking at, what they're looking like. But if you're doing that, then it becomes even more challenging. Get rid of the delays. So application. So this TNA has connected with an EU project. The TNA actually started before the project actually kicked off. So in some ways it was preparing for it, but in other ways also it was doing the fun things that we couldn't get the funding for from the main project. What we've got funding for in the main project is connecting up sites in Germany and Italy, and also some VR sites here at Salford, and being able to support distributed command and control or operation planning, mission planning, and distributed space science. Now, this application's a very nice example, because what happens at the moment is people all go to one place to do the mission. So they're operating the mission from one place, they're starting the science from one place, and then they go back to their respective countries and try and keep everything going. But it doesn't work very well when they go back to their respective countries. All they do is concentrate on their own aspects with their own simulators and lose sight of everything else that's going on. So the real joined up stuff works a lot better in these face-to-face prolonged meetings, which might go on over time when they become distributed. So we're very interested in sort of beaming these people together, to steal a UCL phrase, beaming the scientists not only together but onto Mars. So some of the things we want to be able to do is plan where the Mars robot is going to go. So you might have people in different places, different geographical places on Earth, in sharing the same 3D simulation of Mars, which is built up from real Mars data. This will involve terrain, and people will be able to plan the next 20 meters of the rover. Where is it going to go left rather than right? What's it going to do when it gets to the crater? These kind of things. but also then to be able to analyze the information it's picking up and analyze the information being picked up from satellites and put all these together. So the project we're joining with is very much a sort of an interoperability project. It's about interoperability and distributed workspaces, but it's steering clear of perhaps some of the more interesting telepresence aspects that we wanted to look at. So research, we've spent about 20 years linking immersive VR systems. Now this TNA was perhaps a little bit unusual because it was bringing people to work together before. So that's probably quite unusual. So in particular, Robin Wolf, who's now in DLR Space Science in Germany. So Robin and I have worked together on this for quite a few years. And for about 10 years, we were trying to build a garden gazebo by connecting up highly immersive devices, very often caves, up to 3 caves, also looking at different levels of immersion. We were motion tracking the occupants of each and reflecting their movements through avatars. And we did things like being able to build structures so people could carry beams, wooden beams together. They could drill holes. One could drill a hole in it as the other one held it, put bolts through, this kind of thing. But importantly, they could also use some level of non-verbal communication at the same time. They could use interpersonal distance and how they position themselves not only with respect to each other but the shared objects. So you could show attention and intent. You had head gaze worked quite well. You could tell where somebody was looking, and you could do gestures through arms, etc. But the problem that we had was that almost every link-up that we did, no matter who was involved in the link-up, they all had avatars that looked like Robin. So that was a problem because you couldn't wear special t-shirts. The avatars had different model t-shirts with different badges on them. But the faces were all the same, and also the faces were static. So you didn't know whether somebody was pleased or displeased when you came up with an idea. So in 2009, we got bored with this, and we decided to go down a different road of video-based reconstruction. Now, this is what we now call virtuality avatars. It's what a lot of people have called teleimmersion over the years. We don't call it teleimmersion because we don't think that that distinguishes it from the kind of avatar-based teleimmersion we've just been talking about. So here you have cameras that are surrounding a person, sucking in what they look like and recreating them in some 3D computer graphics form. So you see here a picture of our other facility, the Octave, and there Carl Moore, a recently graduated PhD student who built part of the system, is he's just about to start juggling, and the virtuality avatar in front of him will reflect what he's doing in real time. Now, unlike a standard avatar, everything is a reflection of what's actually happening in that display system. So he's taken balls in, and the balls will be reconstructed. The balls would have been invisible in our old system. If he smiles, you can see him smiling. That video is on YouTube, by the way. Thank you, UCL, for one of these images, which comes from a joint project that we did with UCL, which is eye-catching. So on the one side, in the past, we've been doing virtual avatars. With virtual avatars, you could communicate spatial contexts. in the project that we did with UCL, Reading and Roehampton, we put eye trackers inside shutter glasses and were able to communicate eye gaze as people moved around. But nowadays we are more interested in the virtuality avatars. We've got two versions here. One is Dulcidio, and this is a version that Dulcidio has created a few years ago, actually. So this is using stereopsis. And then at the bottom, this is our latest system using shape from silhouette. But the sharing a spatial context isn't simply about having a 3D medium. It's also got something to do with the dimensionality of the display. So you really need both the display and the medium, which are free viewpoint, where parallax is supported at minimum. But even with that, if you are connecting a flat screen display or two flat screen displays compared to two surround displays like caves, that gives you different degrees of spatial context. In order to be able to walk around the other person and walk around shared objects, immersive surround display systems. We didn't have this available within this project. We had two flat screen display systems, Powerwall display systems, and one large large surround system. So here are the systems we had. So DLR and ThinkLab, they similar setups here with a large Powerwall and motion tracking, and the Octave, which is a large surround 16 projector system. So like any project, you do a bid, you say what it is you're going to do in the bid, and then you actually work out what you're going to do once you've got the money. So we revised all our aims and objectives a little bit in planning. So, and this is basically what we've come out with. So we want to support both virtual and virtuality avatars within a shared Mars simulation. And our objectives towards this is firstly to install the Mars renderer in Salford at both ThinkLab and Octave, integrate the virtual reality avatar, which Robin had already implemented at DLR, and get that implemented over here with motion tracking from DLR driving the avatar in the two Salford labs, and begin the integration of the virtuality avatar. And it was never supposed to finish with the end of the TNA, because the idea of the TNA was to get us to a point where we could then go and do the work in a more distributed way. So what were our challenges? Well, of course, firewalls are one of the biggest ones, as always, but we've also got, we all used different operating systems, different scene graphs, very different capture systems. Capture systems in particular, the motion tracking being used for conventional avatars and surround video cameras for the other. We've got very limited bandwidth in order to be able to send that many video signals. Code integration. Now this code is research code. A lot of it's built up by PhD students, so you can imagine quite how stable it is. So trying to integrate it is fun, it's interesting, and there are no manuals. And how do we integrate this spatial context with the display systems that we have? So here's the Octave system. That shows you the cameras, where they're placed and what they're taking. And we're using a method called shape from silhouette, where we take the silhouettes from each camera and build up a 3D geometry from it, and then texture. At the other end, at DLR, we simply had motion tracking, and this would just be tracking of the shutter glasses and a wand device, and from that you can control an avatar. So here we've got a picture of the avatar working from, so the avatar is being controlled from Germany, from DLR, but it's beaming into the Octave in Salford. So it can actually come into the space in the Octave. This photograph shows it the other side of a wall, but it can actually come in the space with the other person. Now, seeing an interesting flaw of this, our avatar still looks like Robin and is stood next to Robin, which clearly isn't quite correct. So what we forgot to do, because we're idiots, was take a photograph of where we got up to on the virtuality avatar, and I'll explain that in a moment. So anyway, in conclusion then, our aim was to support virtual and virtuality avatars in Mars. We've met all of our objectives. So we've installed the Mars renderer. We've integrated the virtual reality avatar and driven it from DLR, and we've begun the integration of the virtuality avatar driven from Salford. So let's now examine how far we've got with that. We knew we weren't going to get it all finished. We had a choice of either only doing that or doing the Mars render of the avatar and some of this. So that's what we've gone for. So how far have we got? So the reconstruction of the form is working. So we can create a 3D geometry inside the Mars renderer, but it is just a polygonal form. So the textures need to be collected, combined, cut down in a way small enough to get them across the wide area network with the bandwidth we've got. And that some of the problem there is deciding which ones we really need and which ones we don't, and perhaps cutting out bits that we don't need and then combining a texture out of it. We now have a Linux version that DLR can use, so we're now supported on 3 different platforms. We have Mac OS, Windows and Linux, and the Linux version has been tested over in DLR. So the bit left to do really is this networked texturing. We also have, to be able to optimize things, we also have a version that includes mesh compression for the form. So we would like to combine in the mesh compression and the composite texturing. Once we've done all that, hopefully it will work and we can start doing some nice, interesting distributed experiments. We haven't published yet, we've only just finished. We're hoping to put a poster into IEEE VR. Thank you.